And so if you're looking at parallelograms, so here's a couple examples of parallelograms. I'll go through one of them to show the relationship between opposite angles. So again, it winds up being relatively easy if we just measure each of these angles and then identify how the opposite angles relate to each other. So here's angle B, angle C, angle D, and angle A. Again, just selecting the points and choosing measure the angles. And what you can see right here is that these compare opposite angles in any parallelogram are going to be equal. And we can see the same thing with respect to opposite sides. So again, if we just click on those four sides and measure their lengths, we can see that relationship all at once, that these opposite sides here, just like the opposite angles, are equal to each other. And that's true for all parallelograms. Okay. And then finally, the last is the midpoint of the diagonals. So if we connect, remember a diagonal is a segment that connects non-consecutive vertices. So AC is a diagonal, and BD is a diagonal. So here are my two diagonals. If you want to see how do their midpoints relate, well, if I highlight BD and hit Control M identifies the midpoint. Do the same thing with AC, hit Control M. What you notice is it's the exact same point. Okay, so the last relationship is the diagonals bisect each other. Okay, so in any parallelogram, doesn't matter what other classifications it has, but if it's a parallelogram, then opposite angles are equal, opposite sides are equal, and the diagonals bisect each other. Okay, now from the definition of parallelogram, and this is one of the things that can get confusing sometimes, none of these properties is true based on the definition of parallelogram. Okay, the definition of parallelogram simply states it's a quadrilateral with both pair of opposite sides parallel to each other. Okay, these three relationships stem from that, or properties stem from that, and so they're not defining characteristics of it. They're just properties that are true based on it being a parallelogram. Okay, now when we move down, a rectangle is a little more specific type of parallelogram. It's a parallelogram whose angles are what? Angles are right angles. So if we measure each of these, again in this example down below, what you're going to find is, angle A in this case is equal to 90. Angle AEF is equal to 90. Well, since this is a parallelogram, what do we know about angle F? It's opposite A, so it's also going to be 90. And angle B is opposite E, so it's also going to be 90. So again, you can demonstrate those and put all your measures to demonstrate that. Okay, now, if we take a look at the diagonals here, so AF and BE. So here's our two diagonals. If we find their lengths, we see that the diagonals themselves are equal to each other. Now, will these diagonals have the same midpoint? Yeah, because it's a parallelogram. That's not true just because it's a rectangle. That's true because it's a parallelogram. Hey, let's look at these, come back up to this one, again, just to identify. Do you think that AC and BD are equal to each other? Are the two diagonals of that parallelogram equal to each other? If we measure those. No, BD is 7.2, AC is 3.18. Okay, so it's not true that all diagonals are equal to each other for all the parallelograms. It's one of the characteristics that's unique to rectangles. And so if you have a parallelogram and the diagonals are equal to each other, you can use that information to identify it has to be a rectangle. Okay. If you have a parallelogram and all angles are 90 degrees, that's enough to identify that your figure is a rectangle by itself. Okay, the final example to look at is a rhombus, okay, in which case all it's a parallelogram, so all the properties of parallelograms hold true, but the additional property is that all four sides are equal in length. And so that makes it a rhombus. And so here we wanted to look at the relationship in the diagonals. So again, if we construct our diagonals, from just looking at it, does it look like the diagonals are equal in length in this case? No. Okay, so that doesn't have to be true in a rhombus. It's only true for what type of parallelogram? A rectangle, right? So it doesn't have to be true. It might be, but it doesn't have to be. Okay, so let's look at some other things here. If we find this intersection point, one of the unique things, and you can probably see by looking at it, is what angle does it look like is formed here where the diagonals intersect each other? If we want to measure that, does it look like it would be 90 degrees? Yeah, and if one angle of an intersection of lines is 90 degrees, then that means the supplement, the linear pair is 90, the vertical angle pair is 90. So all of those angles are 90 degrees. So when you look at a rhombus, the diagonals are going to intersect at 90-degree angles. Now, we already know from the very first thing that the diagonals share a common midpoint, which means they bisect each other. So when you look at a rhombus, the diagonals are perpendicular and they bisect each other, so that's called perpendicular bisectors. Okay, so in a rhombus, the diagonals are perpendicular bisectors of each other. Okay, and the other thing that they happen to do is if you look at the angle that's formed from a diagonal, so in this case IAH, if I measure that angle and I compare it to BAI, what you're going to see is that this diagonal bisects the angle of a rhombus. Okay, so since opposite angles are equal, BGI and HGI are also going to each equal 30, which you can confirm through measurements. And let's see if it holds true for angle B and H. So ABH, if we measure that, and GBH. Okay, let's see if this diagonal bisected angle ABG. So if we measure that, we see that it does. So what you can see or identify for a rhombus is that the diagonals of a rhombus are perpendicular bisectors of each other and they bisect opposite angles. And so those would be the two relationships. Okay. Do all the properties of parallelograms apply to a rhombus? Yeah, the sides are parallel. Both pair of opposite sides are parallel. The diagonals bisect each other. In fact, in this case, they're perpendicular bisectors of each other. Okay. And then opposite angles, A and G, and then B and H, the overall angles of the rhombus itself, are equal. So all the properties of a parallelogram fit there. Okay, so now it comes time to construct a square. So a square is both a rhombus and a rectangle. So all the properties that we described in here apply to a square. Okay, so the diagonals are perpendicular bisectors of each other, but they're also equal to each other. Okay, it's the rhombus, also the identification from a rectangle. Okay, the opposite angles are equal, opposite sides are equal, that's from a parallelogram. So all of those properties that are discussed in these three examples all hold true for a square. So are there any ideas on how we can construct a square? There's a couple different ways to do it, so I want to see maybe what you guys have come up with. Eddie? So careful on the copy and pasting because you'd still have to identify somehow how it's that length. But if we were to copy it by using a compass, so if we copy this length here, okay, so we know that any other point along here is going to be the same distance as this. Well, at what angle does this other point have to lie from here? Okay, so it has to be equidistant. That's a property of a rhombus. It also has to be at what angle? A right angle, so that's a property of a rectangle. So if we highlight our segment and one of the endpoints and construct a perpendicular, we can find the intersection of that. And so now we know that here's 3 vertices of our square. How can we find the 4th one? It also has to be perpendicular through this point, right? So if we construct another perpendicular here, and then it has to be perpendicular through this point to this line, construct another perpendicular, we now have our 4 points. And so if we highlight these 4 points here and connect that, so if I hit the 3 or those 4 points and hit, now I have my square in solid. No matter where I move any of these points, and only one of the points changes the actual size of it, everything else kind of changes the rotation or length of it. That's always going to remain a square. So that's one way. So this is kind of using the properties that a square is a rhombus because it's equidistant, and it's a rectangle because it's at a right angle. Did anybody have any other ideas on what we could possibly do to create? I'm just going to hide these lines so they're out of the way. Any other ideas on, and I'm going to go ahead and hide this line as well. All right, so here's one potential square. All right, what if we use this concept of diagonals? And so the fact that it's a rhombus means that the diagonals are perpendicular bisectors of each other. And so what if I took, what if I took a segment and we begin with, this segment is a diagonal of the square I'm about to draw. Okay. What would I need to do in order to create the other diagonal? Okay, so the fact it's a rectangle means diagonals are what? A rectangle has diagonals that are congruent or equal. Okay, so we know we have to have another diagonal that's the same length. Okay, and then the fact that it's a rhombus means that the diagonals have to intersect at what kind of angle? Diagonals are 90 degrees. They're perpendicular bisectors of each other. So if I were to construct a perpendicular bisector of this, so it has to pass through the what of this segment? Midpoint. So if I find the midpoint of that segment, and then I construct a perpendicular through the midpoint. So I know that in order for me to find the other 2 points, if I just draw a circle, so there's the equidistant part, and then highlight where those intersect, what I can now do is just connect all 4 vertices, use Control L to create my segment, and again I can hide these pieces, and I'm left with my square. Again, no matter where I move my points, this always remains a square. I could change the size of it or whatever, but it's always going to be a square.